G'day chemistry students, in this video we're looking at, again, dot points 6.3.1 and 2, focusing on titration curves. Let's get into it. To start, I just want to be looking at these 4 titration curves, and they all represent different combinations of acids and bases and express roughly what would be happening to the pH of a solution as the neutralization process is happening. In these graphs, we're starting with the base in the conical flask and adding acid to that flask to neutralize. In this first graph, we see a strong base and a strong acid being combined together. We can tell that it's a strong base because the pH is really high. We know that we're ending with a strong acid because the pH is really low. What we should also be able to see is that as we add acid at the beginning, there's very little change to the pH. Yes, some of the base is being consumed in this process, but there is still an excess of base at this point. Once we hit a point where there isn't really an excess of base anymore, we see a drastic pH change. The equivalence point is in the middle of this sort of turning point or change. And very quickly, once all the base is consumed, we end up having an excess of acid, which makes the pH level plummet. Note that when we have a strong base and a strong acid, the equivalence point hits roughly in the middle, where our pH value is 7. This is slightly different when we have a strong base and a weak acid. We still start with a very high pH because of our strong base. We still need to add acid to be able to get the pH value to decrease, noting that it takes a while for that pH value to start dropping drastically because at that point there's still an excess of base. Once all that base has been consumed though, we see a really big change in pH which skews to that acidic side, but we'll see that that ending pH is nowhere near as low as compared to the strong acid. That's because we're working with a weak acid here. Its ability to drop to a lower pH is limited by its ability to dissociate. What we'll notice though is because our start point and end point are slightly different, that's changed where our middle or equivalence point is. In this case, the equivalence point is above 7. So when we're doing that strong base, weak acid reaction, like we predicted before, the salt at the equivalence point is going to have a pH which is greater than 7. We only start approaching 7 and below once we add an excess of acid, when we add more and more and more acid after the base has been consumed. A quite similar story when we start with a weak base and end with a strong acid. Here we have our weak base pH being a little bit lower compared to where the strong acids were at, say, 13 and 14. We add the acid and begin to neutralize the base, but we don't see a drastic change or our equivalence point until all of that base has been consumed. The equivalence point, we'll note, is lower than 7 because when we have a weak base and a strong acid, as we determined in previous lessons, the neutralized salt is going to have a pH which is less than 7. It's going to be slightly acidic. But as we add more and more and more acid, we're going to find that that pH value continues to dip. Because it's a strong acid, we're going to find that because of the high levels of dissociation, that pH value is going to be quite high. When we combine a weak base and a weak acid together, what we see is that we start at a relatively low pH above 7 with our weak base, and then have a relatively high pH at the end. Yes, it's still going to be acidic at the end when we have an excess of acid, but we're not dipping to those levels like we saw with our strong acids. Note as well that for weak bases and weak acids, the equivalence point is at neutral or near neutral. It just depends on the Ka values when we compare our weak base to our weak acid. Weak base and weak acid titration doesn't serve a massive part of this syllabus or this course, but still something that I wanted to look at and note. A lot of the time as well, just to note, when you do weak base and weak acid titration, you'll find that you sort of get these dips in steps, even more significantly than the dips, or even more frequently than you can see the dips in this graph. And a lot of the time that has to do with sort of equilibrium shifts and the time that it takes for the acid and the base to sort of dissociate and level out. But those kind of concepts go a little bit beyond the confines of our syllabus. Not only can we do acid-base titrations and measure pH changes as we add more and more acid, so that could be using, say, a pH probe. We can also do conductometric titration. So we can do acid-base titration still and react acids and bases together, but rather than measuring the pH of the substance using a pH probe, we can also just measure the conductivity of the solution. And we get some quite interesting graphs. So that's what we're going to be looking at in the last part of this section. The first thing that I want to establish is that our hydrogen ions and our hydroxide ions are the most conductive ions that are present in any of our acid-base reactions. So when there is a lot of hydrogen or hydroxide, you'll see on one of these curves that the conductivity is at its highest. Yes, when we're working with acids and bases, there are going to be other ions, other cations, other anions, but their conductivity when compared to hydrogen and hydroxide, nowhere near as big. So you're probably going to see that there's going to be a dip in conductivity at those points of neutralization where there isn't a lot of hydrogen and hydroxide, but there may still be a lot of the other spectator ions present. When we react a strong acid and a strong base together, what you'll find is that we have a very high conductance with the strong acid. Note as well that we're adding base. So we're starting with acid. So we start with really high conductance because there's lots of hydrogen ions present. As the solution neutralizes though, as we add more base, we see the conductance drop significantly. At the equivalence point, that is where we will see the lowest conductance. That's where there really isn't any hydrogen or hydroxide present, just all the other ions. Once we start adding an excess of base, we'll find that that conductance starts to shoot up again as there is more and more and more hydroxide present. Note that whether we have lots of acid or lots of base, the conductance is high at both of those points, which is a really big difference to the graphs that we saw of which had pH on the y-axis. When we react a strong acid and a weak base together, we start with a high conductance with our strong acid, and as we neutralize, that conductance will decrease until we hit again a low point where there is the lowest amount of conductivity there, meaning that there is very little hydrogen ions at all, just whatever other ions are present. And as we add more and more and more weak base, there's going to be a very minimal change to the amount of hydroxide present. So what you might find is that there might be a little bit of a flat line in the conductance, maybe a slight increase, but the gradient of this line is going to be quite shallow because we're not able to produce as much hydroxide as we did with the strong base because the rate of dissociation for the weak base is significantly lower. Looking at our other two graphs, if we start with a weak acid, our conductance is going to be relatively low compared to what we would see when we add the strong base, where it really starts to kick up. That point where it begins to curve and turn is where we would say the equivalence point is. That's where we're going to start to see a kick up in hydroxide concentration and a big and swift increase in conductance. When we look at having a weak acid and a weak base, what we will see in general is that we have quite a low conductance to begin with, and as we add more and more ions, we might see a bit of a kick in conductivity, but once we hit again that equivalence point, we are going to start to flatten out the curve like we saw for the weak base previously. Again, these weak acid, weak base titrations are not curves that we focus on all that much, but it's still something that we can look at. Keep in mind that the graphs might look slightly different if we start with bases rather than acids, but the curves should still look relatively similar in any case. Thank you very much, everyone. In the next video, we're going to be looking at our last major concept for this module, which is a buffer. And buffers can be used to have a solution maintain its pH even when contaminated with acids and bases. But until then, have a good one.